First speaker of the seminar is Lucas Moll. He's been at the University of Winnipeg, where I am for the last 4 years or so. And he's going to speak today about extremal Squarefree words and variations.
Okay, thanks, Narad. So yeah, thanks for the invite to speak in this seminar, and thanks for organizing. I'm really looking forward to the rest of the talks in the seminar. So just a quick question before we start. Can you see my mouse moving right now? Yes. Or is that just me?
Yeah, we can see it.
Okay, good, because I'll use that to point to stuff. All right, so I'll start by just talking about squares and overlaps. So these are definitions that people probably know. A square is a word of the form XX, where X is non-empty, so like murmur or hot shots. And an overlap is a square plus a letter, where the letter is the first letter of your square. So it's a word of the form AX, AXA, where A is a letter and X is maybe an empty word. So for example, alfalfa is an overlap. And we're most interested in words that don't contain squares or overlaps. So a word is square-free if it contains no squares as factors. And likewise for overlaps. So here's your ABCs of square-free and overlap-free. Apple is square-free, or Apple is not square-free, I should say, because it has this square PP, but it is overlap-free. And banana contains this overlap here, so it's not overlap-free. And it's not square-free either, because every overlap contains a square. And finally, the word clementine is square-free, and you can check that if you have 30 seconds. So those should be familiar to everybody. And these results should also be familiar to everybody, I think. 2A is kind of recognized as the pioneer of combinatorics on words. And he proved that there are arbitrarily long overlap-free binary words, and there are arbitrarily long square-free ternary words. And these results are kind of central to what I'm going to talk about today, because I'm actually going to show that each of these sentences can be extended by a single word. You can put the word extremal in both of these sentences, and they're still true. So I'll tell you what I mean by that. So someone just asked if recordings are going to be made available. Yes, they are. They'll be on the website after. So what I really want to talk about today is the extendability of words. Extremal words are in some sense words that can't be extended and preserve the nice property. So first of all, what do I mean by an extension of a word? If we have a word W, and we'll always work over a fixed alphabet, sigma, then an extension of W is basically a word that's obtained by just adding a letter somewhere in the middle or at either of the ends of W. So here's this formal definition of that. An extension of W is a word W1, W2, where A is a single letter and W can be factored as W1, W2. So in particular, these W1 and W2 could be empty. So just an illustrative example is the English word pans. And over the English alphabet, here are 5 extensions of it. And they all have the nice property that they're also English words. So this one we'll call a left extension because we added a letter on the left. And this one is a right extension because we added a letter on the right. And these ones are all internal extensions because we added a letter internally. So kind of the central question is, given a square-free word W over a fixed alphabet, can we extend W to a longer square-free word by just adding a single letter anywhere we want? Or are there square-free words that can't be extended in this way to a longer square-free word? And of course, you can replace square-free with any property that you're interested in. So that leads to the definition of extremal square-free words. So a square-free word W is extremal if every extension is not square-free. So if every one of its extensions contains a square. So these words were introduced by Gricic, Kordelewski, and Nieuwedomski very recently. And I'll start with just a couple of examples. So I think people will recognize why these two words over the binary alphabet are extremal square-free. It's because they're square-free, and we know that every binary word of length at least 4 contains a square. So that's kind of not too hard to see. Now for the next example, over the ternary alphabet, here's a shortest extremal square-free word. And this is a little bit harder to see unless you have a computer handy, but I'll kind of show you some of the squares that appear when you add a letter. So if you add a letter A on the left, you get the square AA. If you add the letter B, it might be hard to see unless I bracket them, right? The whole thing turns into a square. And if you add the letter C, there's a short square at the beginning. And we could go on to the next position. We get an AA if we add an A, BB if we add a B, and a little bit longer square if we add a C. And so on. So here, if we add an A, there's our square. If we add a B or a C, we get length 2 squares, right? So you might maybe recognize that over the ternary alphabet, you really only have to worry about one letter on these internal extensions, because for 2 of the letters, you're going to get length 2 squares automatically, right? And then at the ends, you kind of have to worry about 2 letters. So this is what extremal square-free words are. I hope everybody kind of has a feel for what they are. And I didn't mention this before, but if you do have any questions or whatever, just throw them in the chat. I'll be watching it. So again, you can replace square-free with any property that you like. So in particular, I'm going to talk a bit about extremal square-free words, a bit about extremal overlap-free words, and then their common generalization in extremal beta-free words at the end. So for extremal square-free words, the first thing you might do is just ask a computer, well, if I search for an extremal square-free word of length n, is there one? And this is what you get for small length. So a natural question is, are there arbitrarily long extremal square-free words over the ternary alphabet? And the answer to that is yes. And Gricic, Kordelewski, and Nieuwedomski showed that. And I'd like to show you their construction because I think it's really nice. They had some very nice ideas there. So one of the keys to the construction that we'll use multiple times is the following lemma. So don't worry too much about reading all the details. I'll just kind of describe to you what this lemma says and how it's applied. So if we have a morphism F and a square-free word U, then this lemma tells us that the word F at U is square-free as long as the following conditions are satisfied. And really the important things about these conditions, the only important thing really about them is that you can check them with a computer once you're given the morphism. So condition 2 is all about some conditions on the images of letters. So they have to be well behaved. And if you give these a read, you'll recognize some of them. And then the first condition just says that every factor of the word U of length at most 3 has a square-free image under F. So basically, all you have to do is check a bunch of conditions on the images of letters and check that the image of every factor of length 3 is square-free. So some people may be saying that this looks familiar. It seems like it's been proved before. It's very similar to a lot of statements, but the difference here is that we're not proving that F preserves square-freeness on every square-free word, just on a particular square-free word. So I don't think that this was actually written down in the literature before. But the proof is kind of similar to some other results that are out there. So we'll use this lemma when we're constructing arbitrarily long square-free ternary words. So the basic idea is to work with some nice building blocks that make the extremal part easy to deal with. So our building blocks are going to be called nearly extremal square-free words. So a nearly extremal square-free word has at most two square-free extensions, one on the left and one on the right. So in particular, it has no internal square-free extensions. And the nice property of these building blocks is that if you take two of these building blocks, U and V, over the binary alphabet, and when you put them together, you get a square-free word, then in fact, the result is nearly extremal square-free. And I mean, this is kind of a 1-minute exercise to do on your own, but I'll just walk you through it because it's a talk and stuff comes fast. So we want to show that UV is nearly extremal square-free. So first of all, it suffices to show that just adding a letter right between U and V, right in the middle, produces a square. Because these things U and V are nearly extremal square-free, right? So you can't add a letter in anywhere in the middle of U without getting a square. And likewise, you can't add a letter anywhere in the middle of V without getting a square. And U only has one left extension at the most, and V only has one right extension at the most that are square-free. So all we have to worry about is right in the middle of U and V. And so if we write U as having X as the last letter and V as having Y as the first letter, then this is the picture that we get. And since UV is square-free, I mean, these two letters X and Y have to be different. So right away, if we try to add an X or a Y in the middle, you get a square of length 2. And since U had only one square-free right extension, it must be UY, right? Because UV is square-free. So if we look at the third letter, Z, it's got to produce a square in UZ even, right? So I hope that everybody is convinced that when you're working with these nearly extremal square-free words, if you put two of them together and the result is square-free, then it's nearly extremal square-free again. So that's why these are nice building blocks. So you can just ask a computer to find some nearly extremal square-free words for you, and this is one of the ones that it'll turn up. It has length 41. And what Gritchik, Kordelewski, and Nieuwodomski noticed, which was pretty nice and pretty convenient, is that, I mean, this isn't just one nearly extremal square-free word, it's 12, right? Because you can permute the alphabet in 6 different ways. So for every permutation pi, we'll let n pi denote the word obtained by applying that permutation to n. And you can also reverse each of those permuted versions of n. Right, and it's not completely obvious, but you can check that you do get 12 distinct nearly extremal square-free words in this way. There's no kind of overlap between these things when you reverse. So now we have 12 building blocks that we're going to work with. And when you start working with these building blocks, kind of the first thing you do is say, well, what happens when I put two of them beside each other? So what happens if I try to put every one of these building blocks after the original word n, which will denote n sub the identity? So I kind of forgot to mention that I'm denoting permutations in cycle notation, but without the commas, just for convenience. So this is the empty cycle, it means the identity. So which permutations can we put after n? You can put n with b and c permuted, and you can put n with a and b permuted, and then reversed. So if you do that for every one of these words, you're led to this digraph where we put an arc from the identity permutation to the permutation swapping b and c, and from the identity permutation to the permutation swapping a and b and reversing the word, right? So you get this nice digraph, which kind of encodes which building blocks can come after which building blocks, right? That's all it says. And preserve this Squarefree property. So then you start looking at this digraph, and it's not too hard to show that you can walk arbitrarily long Squarefree words in this digraph. And what I mean by a walk is just a word over the vertex set obtained by following arcs, right? So one way to see this is you could start at the identity vertex and you could follow this red walk back to the identity, or you could follow this blue one, or you could follow this yellow one, right? So we have three choices. And really all I'm doing is kind of showing you a visual representation of a morphism here, right? We can take any Squarefree word over red, blue, and yellow. And using the Squarefree lemma, we can show that the walk that we get by mapping to these closed walks gives us a Squarefree walk, right? So there's how you can get arbitrarily long Squarefree walks in D. And then, of course, what we're going to do is just take any Squarefree walk and map each vertex to the corresponding permutation or reversal of n. And you can, again, use the Squarefree lemma to just check those finite conditions. In particular, you just have to check every walk of length 3 in the digraph. And you'll see that every Squarefree walk gets mapped to a Squarefree word under this map, right? And because of the nice property of the ends being nearly extremal, and the fact that when you put two nearly extremal words together, as long as they're Squarefree, they'll be nearly extremal Squarefree, we get arbitrarily long nearly extremal Squarefree words out of this construction. So the last thing to do with those nearly extremal Squarefree words is just put some bookends on the ends so that we kind of cut off the extendability. So we find some words P and S, and basically what we prove is that if you take any Squarefree walk and map to the permutations of n, and then put P on the left and S on the right, then you get a nearly extremal Squarefree word. So the property that you really want there is just, you want Pn to be left extremal in a sense, like you want it to have only one Squarefree extension and have that be on the right so that it serves as a bookend on the left. And you want the analogous property for n sub s. So what you can prove is that if W is a Squarefree walk that starts and ends at the identity, then PFW of S is Squarefree. And the Squarefreeness automatically gives you the nearly extremal Squarefreeness because of the nice properties of Pn and S. So that's the construction of Gritchik, Kordelewski, and Nieuwedomski. I thought it was really nice just using the permutations and reversals and using the digraph as kind of a nice visual tool. Really, these are just morphisms, right? But it's very handy to have that in mind. It just helps with visualizing things. So a question you might ask is, are there extremal Squarefree ternary words of every sufficiently large length? Because from looking at the small values, that wasn't clear. It didn't really look like there were a lot of extremal Squarefree words. But we'll see that it is true that there are extremal Squarefree ternary words of every sufficiently large length. In fact, length 87 is enough. As long as you have length 87 or more, you can construct an extremal Squarefree ternary word of that length. So to show that, I kind of like need a snack first, right? I've been talking for 20 minutes already. So Jokes don't really come through via Zoom because I can't hear people laughing or see people smiling. But anyways, people probably have heard this joke before anyways. So chicken McNuggets, you know, they come in packs of 6, 9, and 20. So if you want exactly 16, you're out of luck, right? You can order 2 packs of 9, or you can order a pack of 6 and a pack of 9 and get 15. But you're not going to get exactly 16, right? But it's not hard to show that the largest number that you can't purchase is 43, right? So this is a particular instance of what's called the Frobenius problem. And it's kind of a hard problem in general, but all we really need is a very simple lemma that's kind of the start of the study of the Frobenius problem. So I'll call it the McNugget lemma because it's easy to remember. So it says that if P and Q are relatively prime positive integers, then as long as N is at least P minus 1 times Q minus 1, there exist non-negative integers A and B, so that N is AP plus BQ. So another way to say that is you can express N as a non-negative integer linear combination of P and Q. And this is not really hard to prove. There's some nice, even just proof by pictures of this one. But it is useful when you're trying to construct words of every sufficiently large length, for example. So I'm going to just describe the construction that Nerad and I came up with just in basically a single slide. So what we do is just replace the word N with a set of two nearly extremal Squarefree words Q and R. And these words Q and R have different lengths and they're relatively prime lengths, right? And I have this short factor in red just because you can obtain R from Q just by adding that factor. So that's how we found these two words. So essentially, the idea of the construction is just to use the same digraph, take the Squarefree walks in that digraph, but instead of mapping to the corresponding permutation or reversal of N, you can choose Q or R, the corresponding permutation or reversal of either one of those words. So to prove that this actually works, we had to extend the Squarefree lemma to substitutions. So I won't go into the details of that. But then that gives us nearly extremal Squarefree words of every sufficiently large length by the McNugget lemma, because Q and R have relatively prime lengths. So in particular, we get an extremal Squarefree word of every length at least 2040 by taking a Squarefree walk in the digraph and choosing the appropriate number of Q's and R's to replace each vertex with. And then the last thing we do is we find bookends P and S, and these ones both have the same length. And that's important because one of the other kind of minor tweaks that we had to do was we don't want to walk just starting at the identity vertex. We want our walk to, end possibly anywhere. It could begin or end anywhere. And so you have to kind of suitably permute and reverse P and S, and you have to switch them for the reversed ones. So we needed these bookends to be the same length. So anyways, you take your Squarefree walks, you replace with Q's and R's, and then you bookend with P's and S's. And you get an extremal Squarefree word of every length at least 2,138. So that's great. And then to get the rest of the lengths, we found a bunch of similar constructions that worked, but we didn't feel the need to write them down. And then at the bottom, we had to do some brute force searches. And one of them took I think for length 87, it took a month or something. It took a long time, but I wasn't using a very fast algorithm. So that's that. So we get extremal Squarefree ternary words of every length at least 87. And it's not hard to tweak this construction to show that actually it's not just, a small number of extremal square free ternary words that we have, it's a lot. It grows exponentially. And you can see that just by going back to the square free walks, where we had this choice of red, blue, and yellow cycles. Because you can take any square free word over red, blue, and yellow, and you get the exponential growth out of that. So that's kind of what we know about extremal words, extremal square free ternary words. But what we don't really know a lot about is extremal square free words over larger alphabets. And Grichuk, Kordelewski, and Nieuwodomski actually conjectured that there are none. And I think this is a pretty cool conjecture. To me, it certainly seems true, but it also seems quite difficult to prove. Because in fact, what you're showing, if you could show this, it would say that if you have an alphabet of size at least 4, then every square free word over that alphabet can be extended to a longer square free word just by adding a single letter. And that seems like a pretty strong statement to make. But it also seems like it could be a useful property of square free words over larger alphabets. So I would really like to see a proof of this conjecture. So that's all for extremal square free words for now. So I'll talk a bit about extremal overlap free words. And there we're going to look at the binary alphabet mostly. So as before, an overlap free word is called extremal if every one of its extensions contains an overlap. So we'll ask kind of the same questions that we just answered for extremal square free words over the ternary alphabet. Are there arbitrarily long extremal overlap free binary words? And if so, can you construct an extremal overlap free binary word of every sufficiently large length? And kind of, you could ask about their growth rate too. So with Narad Rampersad and Jeffrey Shallett, I characterized the lengths of the extremal overlap free binary words, just like for extremal square free words. And so the answer to the first question here is yes, you get arbitrarily long extremal overlap free binary words. In particular, you get every sufficiently large even length, but you don't get all the lengths. You don't get every sufficiently large length because you only get these few extremal overlap free binary words of odd length, right? The powers of 2 plus 1 and 3 times the powers of 2 plus 1 for a large enough exponent. So I'll give you a brief description of kind of how we proved this and some of the constructions that went into it. And you can probably guess that we're going to use the 2A Morse morphism, mu, and people know that definition, I think. And we'll call the fixed point of this morphism the 2A Morse word, right? So the first lemma that we kind of use, the first observation that we made is that when you're working with overlap free words, their structure is pretty strict, right? And so if you try to extend an overlap free word anywhere near the middle, like anywhere that's not close to the left or the right, you're going to get an overlap. So in fact, if you look at any overlap free word of length at least 10, and you factor it so that the two chunks are both of length at least 5, then for every letter, if you try to put that letter in between W1 and W2, you get an overlap. So what this says is that if you're looking for an extremal overlap free word, all you have to do is check kind of the left and the right and the first 4 positions on the left and the right. And to prove this lemma, I mean, you can just do it by computer because all you have to do is check the lemma statement for every overlap free word of length exactly 10. And that's enough context. Just having 5 letters on the left and having 5 letters on the right, it's enough context to get an overlap in every extension that you put right in the middle. Okay. So this kind of suggests that extremal overlap free words will be a little bit easier to deal with than extremal square free words. So for the even lengths, first of all, we want to get every sufficiently large even length. So to that end, we'll define earmarked words. So a binary word W is called earmarked if it satisfies the following three conditions. And the first is just that it's overlap free. And then the second and the third just kind of prescribe a specific prefix and suffix for the word. And you can maybe see where we're going here. Like I just told you that all the extensions in the middle automatically produce an overlap. So really, we only need to pay attention to the ends of these overlap-free words to show that they're extremal. So if we look at this earmarked word U, so it's overlap-free and it's got prefix 0010 and suffix 0100. Then if we take its image under the 2A Morse morphism, we'll call that V. And then we'll let W be the word that's obtained just by swapping the first and last letter of V. Then the claim is that the word W is earmarked and extremal overlap free. So I'll briefly justify this to you. To see that it's earmarked, well, first of all, it has a prefix 1101 that is right, and it has a suffix 0100, that's good. So we just need to check that it's overlap free. And since U was earmarked, it must have been overlap free. And the 2A Morse morphism preserves that property, so V must be overlap free. So if W contains an overlap, it's got to be either a prefix, it's got to contain the letter 1 here, or it's got to be a suffix, it's got to contain the letter 0. But if you look at this prefix here, it's easy to check that this prefix never appears again in the word W, just because of the property that V is overlap free. So if it has an overlap as a prefix, it's got to be really short, and you can check that that is not the case. And a similar thing happens with the suffix. This factor doesn't appear again. So we can't have an overlap appearing as the suffix of W. So this word W is earmarked. That's great. And to see that it's extremal overlap free, well, like I said, you just need to check a few positions. So the left and these first 4 positions, and the same thing on the right. And we've got now a prefix and a suffix of length 8. And it's easy enough to check by computer or by hand that you get an overlap just from those first 8 letters or last 8 letters when you add any letter here. So that gives us a way to construct an extremal overlap free word of length 2n from any earmarked word of length n. So maybe you see why we called them earmarked words now, because we have this way to map these words to extremal overlap free words. And in fact, we map them to other earmarked words as well, right? So this does suggest kind of an inductive approach, but notice that this construction only gives you earmarked words of even length, right? So we do need to find earmarked words of odd length at least to get some sort of induction started, right? And for this, we can use Walnut. And I think this is really one of the perfect contexts to use Walnut in, because you could probably show that there are earmarked words of every odd length by some case-based argument, but it probably wouldn't be that interesting, and it would be a lot harder to follow than the proof by Walnut. So if anybody doesn't know, Walnut is a free software program. You can download it here, and these slides are available on the conference website or the seminar website. So Walnut is a free program that can prove or disprove certain statements written out in first order logic. about automatic sequences. And fortunately for us, the 2A Morse word is an automatic sequence. So we can prove the following using Walnut, that there's an earmarked word of length n, as long as n is at least 10 and it's not 0 mod 4. So in particular, we get every odd length for an earmarked word. So we just asked Walnut, for which n does the 2A Morse word contain a factor u of length n minus 4 so that the word u0100 is earmarked? So we kind of have to add this suffix at the end to make this work. So when we ask Walnut that, when we write this out in first order logic, it returns the following automaton. And this automaton reads n in base 2, most significant digit first. And here are our 2 accepting states. And if you look at this automaton long enough, you realize, well, as long as n is large enough, at least 10, then we end up in these 3 states. And the only way to get to the non-accepting state is to have 2 zeros in a row. And that would make n equal to 0 mod 4. So using this construction of earmarked words of all the odd lengths and using some induction, we do need it to get these lengths that are equivalent to 0 mod 4. You can prove that if n is even, then there's an extremal overlap free binary word of length n, as long as n is sufficiently large. Okay, so that covers the even lengths in this theorem. And for the odd lengths, I won't go into a whole lot of detail, but maybe I'll ask if someone's quick in the chat, do you recognize these numbers, 2 to the k plus 1 and 3 times 2 to the k plus 1? Do you have any suspicions about why these lengths might be popping up? Nerad and Jeff aren't allowed to answer, obviously. Jeff says, oh darn. No, do these ring any bells? People are probably just like scrambling for the chat or something. 2 to the k plus 1 and 3 times 2 to the k plus 1. In the context of overlap-free binary words, do those numbers mean anything? Because this is the same question that we asked ourselves. We were like, why would this happen? Why would it just be these lengths? By special words in 2A Morse. Is that true that those are the lengths of bispecial words? So that probably is true. It's also the lengths of the squares in 2A Morse. And that was really the key for us. So thanks for guessing, Julien. So yeah, it's the lengths of squares in 2A Morse, or more generally, it's the lengths of overlap-free binary squares, plus 1, right? So this theorem of Shelton and Sony describes exactly the overlap-free binary squares. They're kind of the squares in this set A, together with all the images under any number of iterates of the 2A Morse morphism. So you get that the overlap-free binary squares are exactly the conjugates of the words in this set. So in particular, since we started with words of length 2 and 3 times 2, and we apply a 2 uniform morphism, the overlap-free binary squares have length 2 to the k or 3 times 2 to the k for some k. So kind of the key to proving that you only get these lengths is showing that if you have an extremal overlap-free binary word of odd length, then it looks like a square plus a letter, basically. And you can prove that using this characterization of the overlap-free binary squares and the factorization theorem of Restivo and Salimi. Those are the key tools. So once you have that kind of structure for the overlap-free binary words or the extremal overlap-free binary words of odd length, it's not too hard to construct them. So that finishes off this theorem that characterizes the lengths of extremal overlap-free binary words. So you might ask, can the extremal overlap-free binary words themselves be characterized? So we characterized their lengths, but maybe it's possible to actually describe exactly what the words are. And then a couple other interesting questions. Are there extremal overlap-free words over any larger alphabets? Just like with the extremal square-free words, it seems that when you move to larger alphabets, you get none. And then the last question, which I'll talk a bit about, is are there extremal cube-free words over the binary alphabet? And what about fractional powers between 2 and 3? So we've seen that if we make the alphabet larger, we don't seem to get any extremal overlap-free words. And now we're going to look at making the powers larger and see what happens there. So we'll talk about extremal beta-free words just in the last 5 minutes. So this definition is probably familiar to people. If you let W be a word where the WIs are letters, then we say that W has period P if it repeats itself every P letters. So if WI plus P is equal to WI for all I that makes sense. So for example, the word alfalfa has periods 3, 6, and 7. And you can check that it has period 3 just because we have ALF and then ALFA. So it's just ALF repeating itself over and over. And the exponent of W is its length divided by its minimal period. So the smallest period of alfalfa was 3, and its length is 7, so it has exponent 7/3. So again, we're interested in words that don't contain these words of large exponent, right? So we say that W is R-free if it has no factor of exponent greater than or equal to R. So for example, square-free words are exactly the 2 free words. And we say that W is R plus free if it contains no factor of exponent strictly greater than R. So overlap-free words are 2 plus free words. So from now on, you don't have to worry about it too much, but I'll just let beta be either a real number or a real number with a plus. And kind of the inequalities are exactly what you would think. 2 plus is just bigger than 2. It's smaller than all numbers bigger than 2. Right? It's just easier to just kind of combine these two notions into one. So a beta-free word is called extremal if every extension of that word contains a factor of exponent at least beta. And the central question that we'll ask is, over a fixed alphabet, for which beta are there arbitrarily long extremal beta-free words? And a logical place to start here is the binary alphabet. So we've already seen that there are arbitrarily long extremal overlap-free binary words, or 2 plus free binary words. And we actually noticed that in some of these extremal overlap-free binary words, every extension actually contained not just an overlap, but a really short overlap, right? So we found that we had a bunch of extremal overlap-free words whose every extension contained a factor of exponent at least 7/3. And this kind of led us to the following definition. If you take 2 extended real numbers, alpha and beta, and alpha is less than or equal to beta, then we say that W is alpha beta extremal if it's alpha free, but every extension of W contains a factor of exponent at least beta. So it's even stronger than alpha free, right? Because it's alpha free, but when you try to extend it, you get a factor of exponent even bigger than alpha. You get a factor of exponent at least beta. And this is a useful idea because if W is alpha beta extremal and gamma is between alpha and beta, then W has got to be extremal gamma free for every one of those gammas. So this is kind of the way that we proved the following theorem. So this was again with Narad Rampersad and Jeff Shallett. So we proved that as long as beta is between 2 and 8/3, then there are arbitrarily long extremal beta-free binary words. And we did this just by kind of breaking this interval from 2 to 8/3 up into 5 chunks and showing that there are arbitrarily long 2 plus 7/3 extremal binary words, for example. So these are overlap-free words whose every extension contains a 7/3 power. And so for part 1, I kind of already described how we found this. We just noticed that in some of our extremal overlap-free binary words that we had already constructed, you got a 7/3 power when you extended the word. And for parts 2 to 5, we just went back to the building blocks and bookends idea. So I think I'll kind of skip that because I'm running out of time. But we essentially adapted the idea of having these nearly extremal building blocks. So we found 3 of them, and we found some bookends that we could put on the end. So that, say, we got a 7/3 plus free word whose every extension was containing a factor of exponent at least 17/7. So in that way, we proved that there are extremal beta-free binary words for every beta from 2 to 8/3. Okay, so the question is, what if beta is bigger than 8/3? And what about larger alphabets? So here's kind of a vague guess. And I think there's room for lots of future work here. So I'll let Bn be the set of beta in the extended real numbers so that there are arbitrarily long extremal beta-free words over n letters. So we just saw for the binary alphabet that at least this interval is included in Bn. And by this half open circle, I mean 2 is not included, but 2 plus is. And likewise, 8/3 is included, but 8/3 plus is not. So we're fairly confident that this might be actually exactly Bn for n equals 2. But we're not confident at all about what this set looks like for larger alphabets. We're not even sure that it's necessarily an interval. And you might recognize these numbers: 7/4, 7/5, 5/4, 6/5. That's the repetition threshold for n letters. So we do think that there are extremal repetition threshold plus free words over the n letter alphabet for all n. And it would also be interesting to figure out kind of what these upper limits seem to be. That would be another repetition threshold that might be interesting to study. So I know it's the first seminar, and people are just kind of easing into this idea, but I'm going to assign some homework for next time. I want you to think about one of these problems that I've mentioned throughout the talk. And I think it would be nice to come up with even incremental progress on any of these. So replace a 4-letter alphabet with a 10-letter alphabet and see what you can do. Or replace 8/3 plus with cube free and see what you can do over the binary alphabet. So yeah, I'll end there. Thanks.